Thank you. So thanks for the invitation. I'm very happy to be here, and Happy New Year to everyone. And yes, so if you look at my abstract on the web, you'll see a completely different title and rather different description. But sort of after talking to a few people here and listening to the evening lecture by Samnath, I realized that there's not much point in talking about symplectic homology if most people have not seen Hamiltonian Floor theory yet. So I'm going to spend today's lecture, at least, and maybe part of the next lecture, depending on how things go, on first describing this in some detail. So I'm really trying to make this useful to you. So if I'm going too fast or too slow, interrupt me, ask me questions, tell me things. So yes. So what's Hamiltonian Floor theory? Well, let me start slightly differently. So one interest in symplectic geometry is that it's connected to very many different neighboring subjects. So we've already seen a few of these connections. So if you look at symplectic geometry, then it's certainly connected to things like differential topology. An example of that being the talks by Michael Sullivan, who sort of related or sort of studied knots and Legendre knots sort of using symplectic techniques. And also sort of because every algebraic variety over C or every Kähler manifold naturally comes with a symplectic form, it's also connected to Kähler and algebraic geometry. And we are the theory of Gromov-Witten invariants, and also to sort of some aspects of quantum physics. But actually, sort of the initial development of symplectic geometry came from a completely different area, which hasn't been talked about very much so far, at least while I've been here, and that's from the theory of dynamical systems. And more precisely, sort of the theory of Hamiltonian systems. So in some sense, the starting point of symplectic geometry was the goal to understand Hamiltonian mechanics in a sort of more conceptual framework. And sort of the most famous and probably the most interesting Hamiltonian system is sort of the n-body problem. So if you neglect friction and relativistic effects, then the motion of the planets is a conservative Hamiltonian system. It's a conservative dynamical system. So many of the problems that we're still sort of dealing with today in sort of in other contexts were first studied or were first posed in this question. So what do you need for Hamiltonian mechanics? So in the modern formulation, we start with the symplectic manifold. And then we give ourselves a function, h, which is usually called the Hamiltonian. So if you're doing classical mechanics, that would be like the energy of your system. And then from the symplectic form and this function, you get a vector field, namely the Hamiltonian vector field. xh, defined by the equation that if I insert xh into the symplectic form, by which I mean I sort of put it into the first slot, then what I'm left with is a one form, and this one form should be minus dh. Right, this, or sort of starting the other way around, the differential of h is a one form, and since omega is non-degenerate, any one form is dual to a vector field. And so xh is the vector field dual to minus dh. And this is a good place to make a general comment. So there are many sign conventions in this subject. So here I put a minus sign here. Other people might put a plus sign there, and then there are a bunch of other conventions that will come up later. And when you read about this subject, almost no two sources completely agree on these conventions. So you have to be very careful when you read about this to make sure sort of you identify sort of what's the same, what's different. And so I've given you a few things as background. So this Flow homologies with applications is a recent survey written by Alberto Abonandolo and Felix Schlenk. So this is maybe the closest in spirit, at least sort of some sections of this are the closest in spirit to what I'm going to do today. So they start even more basic. They start with Morse theory, and then they do what I'm going to do today. If you want to get a little more detail, or sort of maybe still the standard reference for this subject is our Dietmar Salomon's lecture notes on Flow homology. So these were from a summer school at Park City 20 years ago. So they're published as in book form, but you can also find them on his webpage. And then if you want even more details, then you can look at the book by Michel Audin and Mihai Damian, Morse theory and Flow homology. So, and even these don't agree on the conventions. So you have to, there's a general warning, sort of, if you want to read something about this subject and you read from different sources, you have to be very careful to make sort of the connections. Okay, so anyway, my convention for this Hamiltonian vector field is this, and so the flow of this vector field, so if xh is complete, right, when you have a vector field, you can ask about completeness, existence of integral curves. So say if M is compact, then this will always be complete, then it generates a flow. So this is phi from M times R to M, right? So solving the equation that phi t dot should be xh of phi t, right? And then put some initial conditions, and then you get time t max for all t. And in local coordinates, in local Darboux coordinates, P and Q, where omega is summation dpj wedge dqj, this flow equation takes the form Q dot is equal to dh dp, and P dot is equal to minus dh dq. So these are Hamilton's equations as you know them from classical mechanics, if you've ever taken a course. And so this would be sort of the local case, say, in R2n. And so this is sort of the more invariant abstract formulation on a general symplectic manifold. Yeah? I'm sorry? Just a function. Just, I mean, so typically, so in physics, you would choose a very specific M and then a very specific H, which sort of describes your system. So, for example, if you take as M the cotangent bundle with its canonical symplectic form, and then you take as H 1/2 norm of the fiber coordinate squared. Then the system you would get would be the cogeodesic flow. So the orbits would be exactly sort of lifts of geodesics on the base to the cotangent bundle. So that's one standard example. And in general, I mean, this is sort of a Hamiltonian that only has kinetic energy, then you might add a potential term, or you might do other things. Right, so that would be sort of, so typically classical mechanics you would think of as happening on a cotangent bundle, but you can do the same on a general symplectic manifold, and this does come up. Other question? All right, so slightly more generally, so if we were only interested in time-independent functions h, then my talk would be over very quickly. So more generally, we consider time-dependent functions h. So these would be functions h which depend on a time parameter, let's say 0, 1 times m into r, right? And then for each t in 0, 1, we still get a usual function. So for each t, we can still use this equation here to translate, sort of convert the differential of ht into a vector field. So we get one parameter family of vector fields x ht. So ht would be like function from m to r, which is just ht of x is h of t and x, right? And so for each one of these functions, I can do the same trick. So I get a family of vector fields, and in good cases, say if M is compact, or closed better, then we still get, well, it's called a flow, but it's the flow of the time-dependent Hamiltonian, but it's not really a flow anymore. See, for a flow, it still solves this equation now with xh replaced by ht, but it doesn't have the flow property that it's a homomorphism from R into the diffeomorphism group, right? So that is lost, but still, so we still get the flow phi t. So for each t, we get a map from M to M. All right, and my first definition, well, I mean, I already defined a few things, but so the first sort of important definition is a Hamiltonian diffeomorphism of a symplectic manifold M omega is any diffeomorphism that can be written as phi 1 of such a time-dependent family. Well, maybe I should put the h here, right? So this depends on some function or family of functions h for some time-dependent. Family of Hamiltonian functions, right? So you might, I mean, if you want to think of this in terms of physics, you might think of some periodic excitation or something that it sort of adds or subtracts energy to your system, and that's sort of that's the time dependence of your function here. Yeah. So it's still. So it's still defined by this equation. but it's not a flow in the usual sense that a flow would be something that satisfies that phi t plus s is phi t composed with phi s. But now since my h is time dependent, this differential equation is no longer time shift invariant, so this property will get lost. So people usually leave off the quotation marks. I just wanted to make the point that it's not the usual kind of flow that you think of when you think of flows, but it's still called the Hamiltonian flow. All right, and now, yeah. Well, it should, for me, it should be smooth. Yeah, I mean, I don't want to get into sort of too much trouble, so I'll just keep it nice and easy. Let's keep it smooth. Right, and so it turns out that these Hamiltonian diffeomorphisms form a group. And these are sort of that group is sort of the interest, the object of study in some sense. So one thing I should have pointed out is that the flow of a Hamiltonian flow of this form has many nice properties. So if the function is time independent, then xh is actually tangent to the level sets of h. And so it's sort of very different from a gradient type flow. It's really sort of tangential to the level sets. And now if you have a time dependent h, then there's no more, you don't have a level set to speak of. So that property gets lost. But still, in both cases, the other good property that the flow has is it preserves the symplectic form. And so in particular, it preserves the volume on your symplectic manifold. And so the question is, sort of very vaguely, do Hamiltonian diffeomorphisms have interesting properties not shared by all volume preserving or even all symplectic diffeomorphisms. That's sort of the guiding question that we're trying to address. So, and that was sort of one specific way to phrase this question was Arnold's conjecture. That says, for all Hamiltonian diffeomorphisms, the number of fixed points of phi should be at least as much as the minimal number of critical points of a function, of a smooth function on M. And I guess I should say for M closed to be on the safe. I mean, otherwise I'd have to modify this. And moreover, if all fixed points are non-degenerate, I'll say what this means in a second, then the number of fixed points of phi should be, for any Hamiltonian diffeomorphism, should be at least should be bounded below by the minimal number of critical points of some Morse function. Right, so these are Arnold's conjecture in this particular setting. There are other Arnold conjectures. Arnold was very influential in the sense that he raised many interesting questions. And so this is the one that concerns us today. So I should point out what non-degeneracy means in this context. So if x is a fixed point, then d phi is a map from the tangent space of x to itself, right? I mean, because x is a fixed point, and so x is non-degenerate if the differential at x does not have eigenvalue 1. So does not have 1 as an eigenvalue. Alternatively, if you want to think more geometrically, what this says is that if you look at the graph of phi in m times m, it should be transverse to the diagonal at x, at x comma x. Right? So that's non-degeneracy. And that's sort of the obvious analog of non-degeneracy for functions. Right? I mean, the differential of a Morse function also has this property. It's transverse to the zero section of the cotangent bundle. Okay, so does not have 1, the number 1 as an eigenvalue. So I guess, yeah, you prefer that? My German ones look like this. Sorry. Okay. Did I miss anything? No, I think this is fine. Right. And so basically what Fleur theory does is provide one slightly weakened state sort of solution to the second, or proof to a slightly weaker statement of the second form. So to deal, I should point out that if you have a Hamiltonian diffeomorphism, so I said it's a time one map of some time-dependent family of functions, actually, given one Hamiltonian diffeomorphism, there are many such families of functions. So this family HT is not unique in any way. And so in particular, one can always so given a Hamiltonian diffeomorphism, one can always pick the family HT such that it extends smoothly to a time periodic function on R. Right, so they're one periodic in this T variable here. And then we can talk of the the Hamiltonian flow now as a, for all time T. And fixed points of my original Hamiltonian diffeomorphism that I was interested in correspond to time one periodic maps, periodic orbits of this thing, right? fixed points of phi correspond exactly to solutions of the following system. Gamma dot of t should be x ht of gamma of t, and gamma of t plus 1 should be equal to gamma of t. Right. And now it turns out that such one-periodic orbits are actually critical points of a function on the loop space. Well, at least most of them, the one we're interested in. So the most let me say, I'll say what I mean by most interesting in a second. Are critical points of a functional AH from the space of contractible loops. So L0M are loops, so they're maps from S1, which I think of as R mod Z, to M, and gamma should be contractible. Right, so that's what the 0 stands for, null homotopic. And what's that functional? Well, that functional AH at a point at a loop gamma is you do the following thing. Take the integral. So gamma is contractible. So that means that there exists some map U from the disk into my manifold M, such that when I restrict the U to the boundary, then I get my gamma. That's what contractible means. Right? And so I can take the integral over the disk of the symplectic form, so I'll write that again about the U, and then I can subtract the integral from 0 to 1 of ht and gamma t dt. That's going to be my functional, where U from the disk into M is any smooth map such that U restricted to the boundary of the disk is equal to gamma. And now there's one slight point here. What if I choose a disk and you choose a disk? Why should they agree? Right? And so this is where my first simplifying assumption comes in. So to make this really well defined, we assume that the symplectic form vanishes on the image of any sphere. Just a smooth sphere embedded inside M. So omega on pi 2 of M should be 0, meaning that whenever I have a map from a sphere into my manifold, I pull back the symplectic form, I integrate, I get 0. And once I have this, then if you choose a disk and I choose a disk, then one of us has to reverse the orientation, then we can glue them together to a sphere, and then we get 0. So then we see that our values have to agree. So then this is a well-defined function. It turns out that this assumption here well, it can be removed. I'll say that maybe at the end once I've described the whole construction. And it also comes in crucially at another place in our argument to simplify things a lot. So if we don't have that assumption, then we will also have a headache later on that we have to deal with, which we won't have to deal with today. So, any questions so far? Oh, to the Hamiltonian, so to the group of Hamiltonian diffeomorphisms. So given any Hamiltonian diffeomorphism, I can always find the family of functions such that sort of when I do this construction that I did before that generates this, such that this family of functions is actually extends to a one periodic thing. Anything that can be written as time one map of a Hamiltonian flow, as I was describing before. So I gave the definition is still here, right? So a Hamiltonian diffeomorphism is anything which is a time one map of some time dependent function. And so all of them they form a group, and I call that group a hem.
So the first condition is that it's already...
No, see, here I'm just having a family from 0 to, which is parameterized from 0 to 1. So if I want to continue it, it might have a discontinuity, or it might have a discontinuity or worse at 1. I mean, if I want to make it time dependent, if I want to make it time 1 periodic, then the value at 0 should be the value at 1, and the derivatives at 0 should be the derivatives at 1, and so on. So there's some work there. It's not completely obvious. Right? I mean, here there's no condition. There's H0 and H1 could look completely different. Yeah, I could have started with that, but yeah. Anyway, other questions? Yeah. Mm-hmm. Oh, that's a good point. So it is. So the question was that sort of. Well, let me rephrase the question slightly. So, can you always find a time-independent generating family for a given Hamiltonian diffeomorphism? And the answer is no. And if the answer was yes, then the whole theory that I'm about to explain would be very boring. But the point is that there are many Hamiltonian diffeomorphisms which do not have time-independent functions. So a typical one doesn't. And to describe an example would take a little bit of time, so I don't want to do it right now, but you can ask me later. Basically, if the family was time-independent, then sort of any critical point of this function h that you have then would be a fixed point, and the linearization at that fixed point would have very special properties, which are not true for fixed points for general Hamiltonian diffeomorphisms. That's sort of the rough reason why not everything can be generated by a time-independent one. All right. Other questions? Yeah. This is very restrictive. So examples. So if your symplectic manifold is closed and simply connected, then you will never have this. So CPN or anything doesn't satisfy this, right? But examples are tori, so T2n, or surfaces of higher genus. So higher in this case means at least one, so T2 was also an example. And then you can take products of these. So you get some examples, but this is a fairly restrictive assumption. And it can be, yeah, so there's much work on relaxing this, but this is sort of the easiest case where sort of you have the least amount of complications. All right? Good. Where was I? So this is my action functional. And again, there sort of the choice of signs there is another matter of convention. And now I want to briefly tell you sort of why, well, what's the differential of this, right? So what the tangent space at some gamma to my loop space these are just vector fields along gamma. Well, I mean, yeah. So I'm doing this in a very simplistic, heuristic kind of way. I'm not worrying about topology. I'm not worrying about smoothness. So I'm thinking really here of smooth loops, and then the tangent space would be smooth vector fields along gamma. Right. So if I have C a smooth vector field along gamma, then what's the differential of my action functional on this smooth vector field? Well, let me draw sort of a very schematic picture. Suppose here is my gamma. I guess this way. And I have my choice of disk U, right? And now, if I want to understand what's sort of the infinitesimal change of the symplectic area, well, basically, what I do is I have my vector field C along, maybe I should use some color. Right, so I have my vector field C, and if I exponentiate that, I get a family of nearby curves, and so the change of total area here will be sort of the infinitesimal change of, so the infinitesimal area of this color which I'm adding. So that turns out to be, so I'm writing here. So I claim that the first term here, if I differentiate that, then what I'm going to get is the integral from 0 to 1. So it's going to be an integral over gamma, and it's going to be the integral of omega of C of t and gamma dot of t gt. Because essentially, yeah, the way, right, I mean, I have this this color here, let's say I have it of size S, then it has two coordinates, one the t coordinate and one sort of the transverse coordinate here, where, and if I take the derivative of its volume with respect to omega, then this is what I get. And then the other term, there's a similar argument that says that, well, for the other term, the differential takes the form, I take dH t on C of t, and I integrate that. Right, again, sort of to understand what the difference of these integrals is, basically I want to understand sort of how pointwise the integral changes, and that's what this tells me. And then I integrate that. And so let me rewrite this a little bit. So let me, I want to, yeah. So for reasons which will be clear in a second, I want to switch these two. So I claim that this is equal to the integral from 0 to 1 of omega of minus gamma dot of t and C of t. And now the second term, remember that minus dH was just omega inner product, sort of the omega inner product with xh. So this term I can write as plus xht, right? And then I'm integrating that. And so basically, if this is supposed to be 0 for all xi, that means that this thing has to be 0, which means exactly that gamma has to be a solution of my equation that I had over there, right? Gamma dot should be equal to xh. Okay, so that's how we see that one-periodic solutions are really just critical points of this functional, if they're contractible. And I mean, one can generalize this functional even to non-contractible loops, but this is a clean statement for contractible loops. And for what I'm doing today, the contractible ones are the only ones we care about. All right. So now you've seen in Somnath's talk how one way to do Morse theory is to sort of start with a function on a manifold and then build a complex where the generators are the critical points and the differential is given by counting flow lines. Now, here, that idea runs into serious trouble, right? So the naive idea is we want to do Morse theory for AH. And the problems are, there are several problems. Some of them are more serious than others. Well, the first thing, obvious thing is my loop space is infinite dimensional and it's not compact, clearly. And so if I have functions on a non-compact manifold, then I have to be a bit careful when I do Morse theory because depending on what kind of function I choose, I might get very different answers. So, but more importantly, this AH is not, it's even worse, it's not bounded from below, not bounded from above. So AH is unbounded in both directions. And what's worse, the Morse indices, if you look at a non-degenerate fixed point, that would be a non-degenerate critical point of AH, Morse indices and Morse co-indices are both infinite. So Morse index is just the dimension of the negative eigenspace of the Hessian. The co-index is the dimension of the positive eigenspace of the Hessian. They're both infinite. So looks like we're in trouble. We don't. So in Morse theory, for finite dimensional manifolds, what we did is that we took as a grading the index, but now if it's infinite, we don't know what to do. And more importantly, sort of naively, the gradient flow. So I said so far I worked with smooth loops, but actually if you want to implement this analytically, you have to make some choices of some Banach manifold of loops and so on. If you do that, then this function will not have a good gradient flow. So it seems like we're dead. There's nothing we can do. But actually, so here's where Fleur comes in. So Fleur was brave enough to do it anyway. So yeah. No, but you can take your gammas can be more and more, can be longer and longer. So you have more and more, you can accumulate, more and more value, right? And if you go backwards, you can also get more and more negative. Right, so that's one. Or also, these disks, right? This is actually, this is a lower order perturbation. This is the main term, and that sort of right. Once you have one gamma, which has some area, if you traverse it n times, then you have n times that area. If you go backwards, you have minus n times that area. So that sort of tells you that you're in trouble. Okay. Right. So. Okay. Right, so what Fleur basically did is he went ahead and tried anyway, but so if he tried it in a smart way, so basically, so if you wanted to do Morse theory, you first have to decide on some metric on your space, right? And so he chose the L2 metric. Which seems to make matters even worse because on L2 the functional is not even defined, right? I mean, if you just have an L2 loop, it's not even continuous, so you don't even know what this means. But anyway, so what's the L2 metric on the loop space? So if you have given any metric G on, in a second I'll specify a specific one, but given any metric G on M, we can set the L2 metric. So we have two vector fields along some given loop, and the L2 metric in a product of these is by definition the integral from 0 to 1 of G at gamma of T of C of T beta of T dt, right? That's the L2 in a product. That's non-degenerate and reasonably non-degenerate. I mean, except for the fact that you're sort of dealing on, you're working on an infinite dimensional space, you have sort of completeness issues, but that's reasonable enough. So now this would work on any manifold. Now we're on a symplectic manifold. We want to choose a G which has something to do with our symplectic form. So we choose our G of the form Gj, which is omega, where I put a compatible almost complex structure J in the second slot. And just for later reference, I want to remark that since we're integrating over a whole loop, we have sort of some t dependence here in the integrand, so we might as well, if we want, we could make this J t dependent. And sort of that wouldn't cause any problems, and this is actually useful later on. So we might as well think of this family of functions being a family which depends on t. This family of metrics. Okay. So maybe I'll write this in parentheses, works with J t dependent. And then once we have this metric, then let's try and see what the gradient is. Well, we have the differential over there. Well, maybe I put this as an exercise. So with this metric, the gradient of AH at some loop gamma is given by J. Well, let me just get my sentence straight. Right, so it's basically J of this term. And the reason is clear. I mean, if you, so omega compatible for an almost complex structure means that I can insert J here in both slots without changing the integral, without changing the value of this thing. And then what I see is that what I get then is exactly the inner product of J of this with Xi for all Xi, and so that's the definition of gradient. Okay, and so So formally, we can think of gradient flow lines for AH as maps U from R times S1 into M, where now I have two variables. I have S here and T here, satisfying the gradient flow equation. So that would mean that ds of U plus J, well, it depends on the point U, dt of U minus xh t of U is equal to 0. That's Fleur's equation. Right, so this is an important change of point of view. Instead of trying to look at flow lines in this infinite dimensional space, which is a loop space, we're looking at cylinders in its finite dimensional manifold M satisfying this partial differential equation. And now why is this good? It's good because this leading term here is nothing but the Cauchy-Riemann operator. So we're sort of basically saying we're looking at sort of zero order perturbations of holomorphic maps. So for example, it's this equation is elliptic, so if you put the right asymptotic conditions, you'll get finite dimensional spaces of solutions. And so now, do I still need this? No, I guess not. So now, the other important point is that now we run an infinite dimensional space, and I already told you that the critical points have infinite Morse index and co-index, so if there were any flow line, I mean, if there was a flow, most flow lines would actually just sort of go from minus infinity to plus infinity and miss all the critical points, right? Because they're sort of, that's just sort of the way the Morse theory works. I mean, unless you're sort of, yeah, I mean, since stable and unstable manifolds, if they existed, would have infinite codimension, sort of in both forward and backward time, most flow lines would miss the critical points. So most flow lines would be sort of go from minus infinity to plus infinity, so that they would have sort of the value of the function, sort of the difference in function value at both ends would be infinite. So that's reflecting the fact that they have infinite energy. So in fact, the second of Fleur's insight was that it's enough to, I mean, you don't care about all flow lines, you just care about the analogs of flow lines connecting critical points. Right? If you understand these and can make a theory out of these, then maybe you're in business. And so now the point is, if we impose the condition that the energy of such a map U, which would be 1/2 the integral of the differential squared, which, because sort of using the equation, can also be written as the integral, the integral of over R times S1 of just the norm of dsu squared. So if we assume, if we impose that this is finite, then any solution to this, to Fleur's equation, has well-defined limits. So if you look at just the arc direction, so if you let S go to plus or minus infinity, then we get gamma plus minus of t, just functions of t, which are one periodic orbits. Of xh, i.e. critical points for AH. And I guess for this to be literally true, I need to impose, so assume from the start that my H is such that I only have non-degenerate periodic orbits in the sense that I defined before. So the fact is, if all periodic orbits are non-degenerate, and we impose this, then we get that. Okay, very good. And so here, yeah. Well, that's a theorem. There's something to prove. Yeah, no. No, I haven't said. Well, I mean, if this is finite, then it's sort of believable that near the ends, ds should go to 0. And then if you look at the equation, that means that this should go to 0. So then somehow you want to converge to a periodic orbit, right? I mean, it's sort of right. I mean, if you want to have an integral over a non-compact space to be finite, then sort of at infinity, the integrand should essentially vanish. I mean, it's not literally an argument, but that's sort of the intuition behind it. Other questions? All right. So now we're here. And right. So there's a good, so basically just sort of scanning, sort of rewriting the definitions I've given so far, it would follow that in this situation, the energy of such a U is equal to AH of gamma plus minus AH of gamma minus. Right, so that's so if you want to know that you've understood all of sort of things that I've said so far, then this should be sort of doable, easy exercise kind of. It's basically, yeah. All right, so how am I doing on time? Yeah, I was afraid this was going to happen, but that's okay. So, okay, so I'm going to state a theorem, and in the theorem I'm going to have a new object appearing, then I'm going to spend probably most of the last 20 minutes talking about that. So the theorem is now the following. For a generic choice of time-dependent H and fixed J, or for a fixed H with non-degenerate orbits, and a generic time-dependent J, the moduli space of solutions to Fleur's equation with fixed asymptotics gamma plus minus is a smooth manifold of dimension. So I'm going to call this moduli space M gamma plus gamma minus, and the dimension is the Conley Zehnder index of gamma plus minus the Conley Zehnder index of gamma minus. And so now, for this, I mean, so the first statement is clear. It's sort of a finite dimensional smooth manifold, but to make sense of this dimension formula, at least I should give you some hint of what the Conley Zehnder index is. Right, but are there questions before I get into that? Okay, good. So, right. So the Conley Zehnder index so what's the setting? The setting is we have gamma is a one periodic solution of a Hamiltonian flow. Right, gamma is a one periodic orbit of some time-dependent Hamiltonian vector field, and let's fix some disk such that the boundary so the restriction of U to the boundary is equal to gamma, and now the disk is contractible, so over U I can trivialize the tangent bundle of M symplectically, right? So there's a unique up to homotopy trivialization, symplectic trivialization of the tangent bundle of M over this disk. And so in particular, we get a preferred symplectic trivialization of the tangent bundle of M restricted to gamma. Okay, because that's the boundary of the disk. And that will depend on U in general, right? But we have one. And now the Hamiltonian flow, as I said, preserves the symplectic form because of that, in this particular trivialization, the differential of the Hamiltonian flow will be a path of symplectic matrices, right? So because the Hamiltonian flow preserves omega, if you look at I'm sorry? So it's a trivialization of this bundle, which has sort of so it's a choice of symplectic it's a continuous choice of symplectic bases along the circle. That's one way of saying it, right? And in that symplectic basis, let me just see how I started the sentence. So because the flow preserves omega, the differentials d phi t, these are now maps from, I can think of them as maps from gamma, tangent space of gamma 0 to the tangent space at gamma of t, right? These will now be in this basis, in this sterilization, they will become symplectic matrices. So we'll have a path A from 0, 1 into the symplectic group with the property that A of 0 is the identity, right? Because for phi 0 is the identity map, so differential is the identity. And A of 1 is d of phi 1. Phi 1 was my Hamiltonian diffeomorphism, and this has the property that doesn't have 1 as an eigenvalue, right? Okay? And now it turns out that so let's denote by delta all the matrices which do have 1 as an eigenvalue. Then it turns out that this is a codimension 1 subset of sp2n called the Maslov cycle. And the fact is that sp star 2nr, which is sp 2nr minus delta, has 2 connected components. And just for later reference, I can choose specific base points in each of these components. One of which contains a plus, which is minus the identity, and the other contains a minus, which is sort of the 2 by 2 block matrix. So if this is in symplectic coordinates, let's say x1 and y1. It has this form, right? Then it's symplectic. And then in the remaining 2 and minus 2, it also minus the identity. Right? So this is a little fact about symplectic matrices. I mean, you can, if you do symplectic linear algebra, you realize that sort of eigenvalues of, well, I'll say a little bit about that in a second. Is there anything else, someone? Yeah. So once I know that my A has its endpoint in SP star, I can connect that endpoint to one of these two matrices depending on which components it's in without crossing delta, right? So And now there's another fact, and I'll try to illustrate this in dimension 2, that there's a continuous map rho from the whole group of symplectic matrices to S1 extending the determinant, the complex determinant, sort of thought of as a map from UN to S1. Right? So UN is a subgroup of SP2N. It's actually a maximal compact subgroup. And so if you think of this, of elements in here really as sort of complex n by n matrices, they have a complex determinant that takes values in S1. And the claim is that there's a way to extend that map to a continuous map on all of SP2N. And it's not the most, yeah. It's slightly non-intuitive, this extension, but there's a specific extension that we choose here, and then the Conley Zehnder index another property that this has. Yeah, so this rho has a property rho of my two special matrices here, which I chose, is plus or minus 1. And which one takes which value depends on the dimension. Right, so in dimension 2, A plus actually would have rho equal to minus 1, and A minus would have rho equal to 1, but then if you go to higher dimensions, they switch. So, and now, I'll try to explain this. Yeah, I'll have some time to explain this in dimension 2. So I just wanted to give you a rough outline of the definition of the Conley Zehnder index. So now, the Conley Zehnder index of this gamma, well, first with respect to U, is now defined to be the following. We take our path A tilde, so that's a map from 0, 1 to the symplectic matrices, which ends at one of these two special ones. And then if we take rho of that path, then it ends at plus or minus 1. So if we square the whole thing, sort of just squaring sort of in C, so in S1, then we get a path which is a loop, which starts and ends at 1. So I'm going to do rho composed with A, square that, and view that as a map from S1 to S1, because now this has closed up, and I'm going to take the degree of that map. Does that make sense? I'm sorry? Oh, because these only take values in plus or minus 1. So if I'm unlucky and I'm ending at minus 1, then it's not a well-defined map from S1 to S1. It's a map from the interval to the circle, which sort of where the ends don't match. So let me give you, maybe if I give the examples in R2, then it will become clearer. And then if you still have a question, then please ask again. Yeah? I'm sorry? And there's a unique homomorphic trivialization. Well, the disk is contractible, so if you trivialize at the origin, then you extend that, and then sort of, since SP2N is connected, that's sort of, there's nothing, there's only one choice, right? So the trivializations at one point are connected, and then there's a unique way of spreading that to the whole disk. Right. So maybe, I mean, this is a kind of a complicated definition, but let me try to explain this in R2. Right. So, and this computation will actually be useful sort of later when I talk about symplectic homology. That computation will actually become relevant. So let's look at the lowest possible case, so n equal to 1. So then we're looking, this row is now a map from SP2 or to S1. And the statement was that, so I claimed that row restricted to U1, which is also known as SO2, inside SP2R is the complex determinant. So rho of some matrix of the form cosine phi minus sine phi cosine phi is just e to the I phi. Right, because that matrix sort of in complex notation corresponds to multiplication by e to the I phi. So that's the, and in general, I mean, there's sort of a symplectic way of saying this. Basically, if you, so if you're a 2 by 2 symplectic matrix, then, so eigenvalues of 2 by 2 symplectic matrix come in pairs lambda and 1 over lambda, right? So either lambda is real, well then this is what they are, or lambda is complex and 1 over lambda is also equal to lambda bar, right? So basically the eigenvalues can take, so if I have my unit circle, then, and here's 1, then my SP2 star basically has two components. One where sort of the eigenvalues are sort of both positive and real, one bigger than 1, one smaller than 1. And here's 0, 0 doesn't appear. And then the other component is where the eigenvalues are either on the unit circle or they're negative and real. Right, so those are basically, if I just look at the eigenvalues, then for one of the components, they land in the yellow stuff, and they appear either like this or like that. And for the other component, they land in the red stuff, and they sort of appear like that. And so, so I just told you that if the eigenvalues are actually on, so if you're, no, I told you that if you're literally a rotation, then the eigenvalues are in a circle, and it's really just sort of e to the I phi. You're really just sort of basically looking at what's the angle of rotation. And it turns out that rho of some matrix which has real eigenvalues, so let's say it's e to the bt 0, 0, e to the minus bt, such a matrix, well, or I don't need a t at the moment. So rho of such a matrix is always 1. turns out. So this whole, so under the map rho, this whole red guy, sort of everything that's above the red guy always all gets crushed to 1. And so then what you can see from this kind of, well, in general, so basically, yeah, so if the eigenvalues are positive real, then rho is 1. If the eigenvalues are negative real, then rho is -1. And if the eigenvalues are complex, then there's a way of picking out, well, then they would be of the form e to the I phi and e to the minus I phi. And there's a way of picking one out of the two by a special property, which sort of corresponds to sort of which way you rotate it, if you have a rotation. And so then rho would be that eigenvalue. And so in particular, if a tilde of t is something of the form cosine at minus sine at sine at cosine at, well, the endpoint shouldn't have 1 as an eigenvalue, so a should not be a multiple of 2 pi. So let's assume a is between 2 pi and 2 pi times k plus 1. Then what we're doing here is sort of, if we just did rho, then we would make k turns and a little bit more. Right? So we start at the identity and we make k full turns and then we turn a little bit more. And so then the rule is sort of, we've turned a little bit more, so then we have to connect all the way over there. And then when we square it, we get as a degree 2k plus 1. So then the Conley Zehnder index is 2k plus 1 in this case. Whereas, sorry, if a tilde is something of the form, now let's say e to the bt, e to the minus bt, for b arbitrary, well, I guess it shouldn't be 0. Then my eigenvalues just move in the red part, so my rho stays constant equal at 1. So then the Conley Zehnder index of gamma is 0. Okay. Does that help in answering the question you wanted to ask before, or was your question a different question? Okay. All right. So, other questions about this? So basically, the intuition you should have is that somehow, I mean, except for the construction of this rho, which you can find in say, actually in another paper by Solomon, I gave you sort of the definition, but the intuition you should have is that somehow this Conley Zehnder index measures the way the nearby flow lines twist around your periodic flow line, right? I mean, so the Hamiltonian flow, this is phi t, moves along gamma, right? Gamma is your periodic orbit, and then nearby flow lines don't close up, but they stay sort of nearby infinitesimally, and so they might make a certain number of turns around, I mean, in dimension in 3, well, I mean, if your energy surface is dimension 3, let's say even h is time independent, then your energy surface is of dimension 3, then sort of the transverse slice is of dimension 2, then you basically have just rotations, and it measures how often your nearby orbits turn around gamma. That's sort of, that's basically And in higher dimensions, basically, in different symplectic directions, you can turn in different directions. So it's slightly more complicated, but still, it somehow measures local twisting of the flow. So the clock sort of ran out on me. So I was kind of, yeah, I kind of knew this was going to happen at some point. So this is a good place to stop. Are there questions? Mm-hmm. No, we're removing more than the identity. So anything that's a shear, for example, is also symplectic, right? If I have any map of this form is symplectic. So I mean, no, it's really a codimension one thing in. So SP2 is what, 3-dimensional, right? It's just SL2R, and the Maslow cycle is really a codimension one. So it's a 2-dimensional subset which really separates the space into two components. Other questions? Yeah. I mean, in dimension 2, this is what this choice boils down to. I mean, it always has. I mean, this property just comes from as part of the defining property, right? So it's supposed to be an extension of the determinant. So on the unitary ones, it's supposed to really just be that. But then, sort of the way you extend it is slightly non-obvious. Yeah, it is unique up to homotopy. Yeah, sorry, I should have mentioned that. So basically, another way of saying this Conley Zehnder index is basically a kind of oriented intersection number with this Maslow cycle, with this delta. Right? If I close up, if I take sort of, if I close up the loop. Mm-hmm. Yeah. Mm-hmm. Yeah. So in the lowest dimension, if you're just sort of where this is 2-dimensional, it's really sort of a kind of rotation number, yeah. Well,
in general, it's just take -1 to the Conley Zehnder index, then maybe subtract n or something. That's the rotation.
no, I mean that you're just once you take -1 to something, you just get a plus or -1. That's just in.
Right, but the rotation number is plus.
No. The rotation. I mean, if you have a.
Fixed point number.
No, you're talking about something different. So there's you can also associate a parity to a periodic orbit, which takes values in plus or -1, and that's essentially -1 to the Conley Zehnder index, maybe up to some correction, depending on. Yeah, you're thinking about the Lefschetz index, sort of the index. I mean the index of the yeah. No, he was talking about the rotation number. But it's really sort of that's specific to dimension 2. All right. Was I going too slow, too fast? Yeah. Mm-hmm. Yeah. So that rotation number. I mean, it's well. I guess you have to. Well, sort of. The way I've set things up, this Poincare return map doesn't have 1 as yet as an eigenvalue. So sort of. I mean, you really have to know the whole path to. So the Poincare return map just as one linear map just really has the index and it's plus or -1, and that's -1 to the Conley Zehnder index plus some correction, but probably -1 or something like that. But right, I mean, if you just have if you just have the endpoint, that's not enough information to determine the Conley Zehnder index. But it still, so the endpoint still retains sort of this parity information.
Actually, I have one.
Yeah.
So here you said this only then that depends on choice.
Right, that's a good point. So That's another remark to make. So there's another simplifying assumption where it doesn't, namely, if you change to a different disk, then that's like taking connected sum with a sphere. And so that, in general, would change the Conley Zehnder index by adding twice the first Chern number of that sphere. So if we assume that C1 vanishes on spheres, then it doesn't even depend on a disk. And that's what we'll do. So next time when I continue, I will assume both that omega vanishes on pi2 and that C1 vanishes on pi2. And so then my action function is well defined and my Conley Zehnder indices do not depend on choices. Yes, so in gamma, so I'm assuming gamma is one periodic solution of a specific system, and with respect to that system, it has a Conley Zehnder index. Yes.
Are there other questions? Okay, if not, let's thank Janko.